Hello students, this is Dr. Ben and we're going to work through another example problem out of chapter 4 that involves the concepts of both force and motion together. And so this is a problem that involves the motion on a ramp or an incline, and the target variable for this problem in the last sentence, second to last sentence, is the tension in the cable that's used to pull this cart down or up a hill. So the tension is a force, and so that probably means we're going to have to do the motion part of the problem first in order to find the acceleration of the object, and then we can use the acceleration and the forces in order to find the tension in this cable that we're trying to do. All right, so if it is a motion first problem, then we're going to have to set up the kinematic to figure out what happens to this object. So we'll need to have a pictorial representation. So I'm going to go ahead and draw that pictorial representation on an incline. In reading the problem, it says that the cart is lowered down the incline. So let's pick our origin of the coordinate system to be at that point I just marked, and we'll put the initial position of the cart to be there and its final position to be there when it's closer to the bottom. And so the velocity is down this hill. We'll call this point number 1 and we'll call this point number 2. And I'll solve this problem using the tilted coordinate system, where x is pointing down the hill and y is pointing perpendicular. So we can go ahead and make our variables for the motion part. So we're going to have an x1, a v1, and a t1, and we'll have an x2, v2, and t2. And since this cart is actually decelerating as it goes down the hill, we're told, because its speed decreases, that means that the acceleration points up the hill. All right, so let's go ahead and make our list of what we know and what we want to find for the motion part of the problem. So the angle is 37 degrees. The speed decreases from an initial speed of 10 meters per second to a final speed of 0. And we're told that the time interval for this change is 5 seconds. We can use the approximate value of 10 meters per second squared for the acceleration due to gravity. We can see in our coordinate system that we've set x1 to be equal to 0, and what I want to find from my analysis is the acceleration in the x direction, so we can use that to figure out what is the tension that's on the cable from doing the force part of the problem. Right, so since we know something about the time that it takes for this cart to slow down as it's going down the hill, it would make sense to use one of the kinematic equations that has the time in it. We're not particularly interested in the car's position, but we are interested in its change in velocity, so the equation that has the velocity, the acceleration, and the time would probably be the best to use. So let's write down that v2 equals v1 plus the acceleration in the x direction multiplied by delta t. So from our problem, the final velocity is given to be 0. The initial velocity is 10 meters per second, plus the acceleration in the x direction that we're trying to find, multiplied by the time interval of 5 seconds. And so we can see, just from doing a little bit of algebra, that a sub x will be equal to negative 10 divided by 5, which is equal to negative 2.0, and that would have units of meters per second squared. So the acceleration of this coal cart as it's being lowered down the hill at a decreasing speed is negative 2 meters per second squared. All right, so now that we've got that done, we can go ahead and to consider the forces part of the problem. So we can find the tension in this cable. So the first thing that I'm going to do is to draw a force diagram for this cart as it's lowered down the hill. So the tension is pointing up the hill towards the motor. The normal force is perpendicular to the hill. The weight force points vertically downwards, and it makes the same angle that the plane makes with the horizontal. And it says that there is no friction in this problem. All right, so let's pick a coordinate system for the forces part of the problem where x points down and y points perpendicular to the hill. All right, so now we're in a position to use Newton's second law in order to find the value of the tension. So we have our force diagram with the tension force, the normal force, and the weight. Let's make our table of what we know for the forces part of the problem. So the mass of the cart is given to be 500 kilograms. We found the value of AX from the first part of the problem, and that was -2 meters per second squared. Our angle is still 37 degrees, and our unknown will be the tension in the cable. All right, so we need to apply Newton's second law, and the x direction is the motion direction, so that's the one that's most important for us at the moment. So we'll say that A sub x is equal to the net force in the x direction divided by the mass of the cart. So that is going to tell us that A sub x is equal to the net force in the x direction will be equal to mg times the sine of theta, because that's the shadow of the weight that points down the hill, minus the tension force, because it points up the hill, we called up negative, divided by the mass. And now I just need to solve this algebraic expression for the tension. So cross multiplying gives me m times ax equals mg sine of theta minus t. So taking the t to the left makes it positive. Mg sine of theta minus m times a sub x, and that will be our answer. So we'll have 500 times 10 times the sine of 37 degrees minus 500 times -2, because we found out that the acceleration was up the hill in the coordinate system we picked, so that was a negative number. So let's see, the sine of 37 is equal to 0.6. So we have 500 times 10, which is 5,000 times 0.6. So that's 3,000 minus 500 times -2, which is plus another 1,000. And so that equals 4,000 newtons. So the tension in this cable as the cart is being lowered down the hill is equal to 4,000 newtons. And just to check, we'll make sure we put our units, tension measured in meters, and our significant figures. We have not too many. All right, so that's another example of a force in motion problem where we needed to do the motion part first.